Hey Wheaton North, Mr. Yergler here. Let's talk about exceptions to the octet rule. Now, as I've said before, there's really no exceptions in chemistry. These atoms are still going to the lowest energy level, but we talk about them as exceptions because our simplistic rule of every atom has to have an octet is kind of overly simplistic. That's not really what's happening. It's really just that atoms are going to their lowest energy. But that aside, we're going to call these exceptions just to kind of make it easy. All right, there's a few cases where the octet rule is violated. These situations are when particles have an odd number of valence electrons. There's a couple examples. If we were to total up, this one's probably the easiest to total up. Oxygen has 6, nitrogen has 5, so that's 11. It's impossible to have an octet rule if you only have 11 electrons because you have one that's not paired. So that's going to be an exception to the octet rule. Also, atoms with less than an octet. So there's only two examples of this, boron and beryllium. You could say hydrogen is also thrown in there as well. Hydrogen always only has 2 because that one has orbital. There is no 1p orbital. This is what boron trifluoride looks like. Notice that the boron only has 3 pairs of electrons. So it doesn't have an octet, and that's okay. This is just kind of follows with what we observe in nature. We'll just suffice it to say that the reason is because it doesn't have enough electrons in the p orbital to hybridize into a state where it can form 4 bonds. It can only form 3 bonds. Its covalency is only 3. You could theoretically, if you really wanted to force it into an octet, you would have to form some sort of resonance structure where you have a double bond. But there's a problem with this. Fluorine isn't going to share more than 1 pair of electrons. For one thing, fluorine already has 7 electrons, and so it's not going to share 2 of its own to help boron out. And this just isn't consistent with the chemical behavior. This isn't consistent with data on the properties of boron trifluoride. We know from its properties that it has to behave, it has to look more like this than like that. Another situation where we aren't going to follow the octet rule is atoms that have more than an octet. This occurs when an atom gains an expanded valence shell. So this is only going to be situations where we have access to the 3D sublevel. Phosphorus pentachloride is an example of this. Notice that phosphorus has more than 4 bonds on it. And this is acceptable because it has access to that third energy level. So we're only going to see this in atoms that have an n equals 3 or higher, so n equals 4 or n equals 5. In the second energy level, there is no d sublevel in order there is no d sublevel to fill, and so atoms can't use it to form multiple bonds. We have to have that unfilled d orbital in order to form more than 4 bonds. We'll see this a lot when we have large central atoms and small terminal atoms or exterior atoms. For one thing, the large central atom allows more physical space to accept electron pairs, and kind of similarly, small terminal atoms can fit more easily around that central atom. So this makes it possible to form more than 4 bonds in some cases. Here's several examples. You don't have to copy all these down. It'll be helpful to notice some of the patterns here. Most of the situations where we have hypervalent compounds is when we have specific atoms like phosphorus, sulfur. Sometimes some of the halogens will do this as well, chlorine and bromine. You won't see this thing with things like carbon and nitrogen. For one thing, they're in the n equals 2 energy level, but also they just don't have enough space around them to form multiple bonds. We can even form some bonds in the noble gases. And again, this is only possible because there's potentially empty d orbitals that we can fill. For example, xenon is in the 5th energy level, but the 5d sublevel has not been filled yet. We don't fill that until after the 6s. When doing Lewis dot structures for these, we're still going to follow the exact same steps. So you still want to total up your number of electrons, start by forming the bonds in between all the atoms, and then fill out the octets of the terminal atoms, and then if there's any left, then you'll put them on the central atom. The thing about hypervalent compounds is that you'll often have extra electrons that you slap onto the central atom, even though it already has 4 or maybe even 5 or 6 bonds. And that's acceptable with some of these larger central atoms. All right, here's an example, PCl5, phosphorus pentachloride. Go ahead and write the Lewis dot structure for this. As always, start with the phosphorus as your central atom, figure out how many valence electrons you need, fill out the terminal atoms first, and then any extras can go on the central atom if there are any. Bring that to class, bring any questions that you have to class, and we'll get more practice there. All right, this is Mr. Yergler, signing out.